Okay, so it's 12:15, so should we start then? Yep, perfect. So it is my biggest pleasure here to introduce, although many of you already know, Dr. Adam Kowalski, our own professor at the APS department. He holds this unique position of 50-50 professors, where he is here at the APS department, also at the National Solar Observatory and LASP. Dr. Adam Kowalski, he received his bachelor's degree, I believe, in 2006 from University of Chicago. And then he got his PhD at University of Washington in 2012 with Susan Hawley. Later on, he joined NASA Goddard, where he was first postdoctoral fellow and then research associate till 2016. And then 6 years ago, he joined here the APS department. And Adam is a recent recipient, last year recipient of the American Astronomical Society Solar Physics Division Karen Harvey Prize. That's the most prestigious solar physics award here of the AAS, so we're very proud. And congratulations, Adam, again. Yeah, that's a big honor. And Adam is one of these unique people who has expertise both in solar and stellar flares. And he's going to tell us more about the research of his research group. Thank you so much, Adam.
Thank you. Thanks, everybody, for coming. Thanks for your time today. Thanks for the organizing committee for allowing me to share my research with you all. And I also...
Before we start, do you hear well, Adam?
Okay.
Yep. Okay,
cool.
perfect. Just to make sure. Yep.
All right. Yeah, let's go. I also want to recognize my collaborators and collaborations, without whom none of this work would be remotely possible. So today I'm going to focus on new model predictions for solar flare spectra for the Daniel K. Inouye Solar Telescope, or DKIST. The DKIST is a 4-meter solar telescope, the biggest in the world. It has just started observations. It's located in Maui and Haleakala. And I will discuss how we think we're now ready with our models to learn new physics about the lower atmosphere response during solar flares. These new model predictions are motivated by recent studies of solar flares using iris data, and in particular, new models of the red wing asymmetry, which I will talk about in spectral lines. And the important ingredient for our new models will be the hydrogen line broadening, which I'll focus on, discuss in a bit of detail. At the end, I will briefly touch on some new results, bringing everything together, modeling the great flare of 80 Leo, which is an M-dwarf flare star, our new models of the continuum radiation and the hydrogen line broadening. That will be pretty brief. These are results that have been submitted or imminently about to be submitted. Okay, so let's start with an overview of the solar atmosphere. Got a lot of jargon coming your way. All right, so please stop me along the way if you have any questions. Okay, don't worry about that. All right, so here is the temperature versus the height above the τ=1 surface for the sun. And the τ=1 surface, which is actually a layer of the atmosphere, 60 to 100 kilometers thick, not a surface, is what we call the photosphere. It's where the visible light originates. And as you go up, you hit the chromosphere, which is the temperature rise, but the density is decreasing. This is about 8,000 Kelvin. And then you have a transition region, a steep jump in temperature up to 1 million degrees, and then the corona, which is the several million degree extended region. And the flare, everything gets hotter. The corona becomes tens of millions of degrees. The flare transition region goes deeper, becomes hotter, denser, and the flare chromosphere goes deeper and becomes hotter, denser. And we liken the flare corona to these flare loops, these wonderful features that we're all pretty familiar with if you've seen press releases of solar flare observations. And these light up later on, actually. They're X-ray emitting magnetic loops with a dramatic increase in density from before the flare. The flare chromosphere shines up as compact brightenings closer to the surface. This is an image now of a different flare. We're looking top down, okay? And we have more jargon here. These compact brightenings we call kernels, the most compact, the brightest sources, and they line up sequentially along ribbons. This is what we call a two-ribbon flare. So one ribbon here and one ribbon there. Let's see, I think my hand might be steadier. Yeah, with the mouse, okay. Yeah, so one ribbon there. At high spatial resolution, obviously, it's not just two ribbons, it's much more complicated, but generally speaking. So here is a more diffuse ribbon, here's a kernel, okay? Now, I could stop the talk now if this was the full story. That is, if temperature was the only thing that changed during a flare. But that is not so. Before the flare, you have approximately a hydrostatic equilibrium structure for the sun. But during the flare, the densities change dramatically. I have some representative densities here, and this is why I have 30-some more slides. And this is why the spectra turn out to be so interesting. Okay, so let's take a step back. Let's look at a movie of a different flare, a very well-studied flare. All right, and this is an H-alpha data from NSO Gong, showing the full disk of the sun. And H-alpha probes plasma 10,000, 20,000 degrees. Flares happen around sunspots. You can't see the sunspot here, but you can see the brightenings around the sunspot, this is what we call plage. Okay, so bright H-alpha regions around sunspots. So I'm going to loop this. We're going to see the flare in contrast to the entire disk, and then I'm going to zoom in on it. And you'll see the two ribbons that form. Okay? And you can see the apparent spreading of the two ribbons over time as well in the zoom in. If you have a good eye, you can actually see a blast wave go out in the full disk view. It's called a Morton wave. So there's a full sun disturbance from these flares as well. I have YouTube links to all these videos. Just email me. You can get these slides, look at them in more detail later on. So the flare is the burst of electromagnetic radiation. We see radiation from the gamma rays, X-rays, to the radio waves. This talk, I'm going to be primarily discussing the optical and the near UV radiation, the thermal signatures from the chromosphere and or photosphere, the lower dense flare atmosphere. Let's take a step back further and put the flare in context. We think the flare is part of a bigger process called a solar eruptive event, which comprises this flare, the burst of light, electromagnetic radiation, and the burst of plasma, magnetic field, and accelerated particles away from the sun, what we call the coronal mass ejection. 80% of the solar eruptive event energy is in the kinetic energy of the coronal mass ejection, or CME. Of the remaining 20%, most of the radiative energy is in the continuum from the near ultraviolet, optical, extending into the near IR, what we call the white light continuum radiation. Goes by many names used in different contexts, but that's what we call it. Actually, in the X-rays, about 1% is emitted, though that's what you typically hear about in terms of a solar flare, the GOES classification, which I'll talk about in a second. In any given spectral line, less than 1% is emitted. The coronal mass ejection, as it erupts from the sun, produces a shock, which can accelerate ambient particles to relativistic energies, and those can reach Earth well ahead of the shock, just after the photons. These are called the solar energetic particles. And all these parts of the solar eruptive event are very important for space weather in their own way. Speaking of space weather, the sun goes through magnetic activity cycles with a period of 11 years. It has maxima in the number of sunspots per month every 11 years, which is correlated with the number of flares per month every 11 years. The last minimum was in 2020, and we're now approaching another maximum, which will be around the year 2025. It's a really important question to answer of when the next maximum will be and how strong it will be. And there are different methods to predict this. The last maximum was really weak compared to the one around 2003 and 1990 and the one before that. The official first prediction by NOAA, NASA, was the blue line here, predicting an even weaker sunspot maximum number 25. And then a completely different method, which was purely empirical, came along from Lemon and McIntosh, which is the red, saying the next maximum should be one of the largest in modern history. They got more data to refine their empirical technique, and they revised it, and that's what you see here, saying it should be more active than previous cycle and comparable to the 2003 and 1990. And the bottom here, I just show a zoom in, and these are continuously updated from these websites. Here's the data, the smooth data in black, compared to the NOAA prediction shifted, and then the McIntosh-Lemon prediction. So time will tell. I think it's really exciting that we have two wildly different predictions almost, right? We're going to learn a lot about the magnetic activity cycle because we have these two competing predictions, depending on what the sun actually does. I don't want to be an alarmist here, but the worst case scenario is still very bad. In the case of an extreme event that hits us just right, our power system is aged, hasn't been updated for a long time, and large parts of the country and globe could lose power for months or even longer. If you don't believe me, check out this recent series by Bill Nye. The End of the World is Nigh, episode 3, goes through this scenario. It's a wonderful series. Of course, he has his characteristic comedic take on 6 end of the world scenarios. But we have very sophisticated facilities at SWPC down the street, Space Weather Prediction Center, CCMC at NASA, and the executive branch is well aware of these issues and have already put in place action plans to update our power grids, aging transformer systems. So don't lose sleep at night, but be aware of the problem. We can sit back and enjoy the physics of flares today. I do like to show a recent image of the sun in white light. This is from yesterday. We have some sunspot groups here, and these are where the flares happen around sunspot. These sunspots are pretty benign because they're nice and circular. They're well separated. They're not really mixed together. The more pretty and circular they are, the more benign, really. Okay? And I show the GOES light curve from the past several days. We had an M1 flare just this morning. So flares are classified by their peak X-ray flux, either in A class, B class, C class, M class, or X class. The largest ever was about an X28 in modern history. So there are a number of X-class flares that occurred in March, and the IRIS mission observed these for us. IRIS is the Interface Region Imaging Spectrograph. It provides high cadence, high spatial resolution, far ultraviolet, near ultraviolet, spectra, and imaging of flares and a variety of other phenomena. It actually was not meant to be a flare mission, but it has been very generous at providing flare data for us, for the community at large, and very skilled at knowing where to point to catch the flare. So I pulled some data off the archives. On the left, I'll show you a movie in the far ultraviolet. You'll see the foot point ribbons, which spread away from each other. And then you'll see the loops that light up connecting the ribbons later on in the flare. So let me play this first, and I'll talk about the right side movie. Okay, so you have the ribbons, kernels, and then the loops. And you can even see the faint slit going down the middle, perhaps. So it just stared at that one region, and they got spectra along the slit in the spatial direction. So on the right, I'm going to stop that. I'll stop it. On the right, I have spectra on magnesium 2H and K in the near ultraviolet. And there's a spatial direction along the slit, and then wavelength, magnesium 2K, resonance line, H, resonance line. And then these are more minor magnesium 2 lines. I'll call them the triplets. All right. I want you to notice a few things. One is that you'll see a broadband continuum increase. You'll see the brightening apparently go this way, in this direction, which traces the ribbon motion this way. And you'll see, obviously, the lines get very bright, very broad. But in particular, you'll see a very prominent redshift in the lines. And this is what we want to understand. This is what we call the red wing asymmetry. Yeah. Okay. Some brightenings. There's the flare, and there's the redshift. And you can see the continuum as well. Okay. I'll let it play again. So there. Very, very broad, highly redshifted. We want to try to reproduce that. So we have to deliver energy to the flare to the chromosphere to do that. Where does the energy come from? Yep, question.
Interrupt and ask a question. Why is it redshifted? If it's coming towards us, I would have thought it would be blue shifted. Flare is coming towards us.
Okay, so there's the coronal mass ejection, which is the material that's erupted away from the sun, which comes toward us. All right, and then there's the explosion in the chromosphere, which is an explosion which propels material towards the lower atmosphere and then into the loops above. So you should see blue shifts and hot lines and red shifts and cool lines. I'll discuss that in a little bit with a nice cartoon. So where does this flare energy come from? Well, we think it comes from the corona, from twisted, stressed magnetic fields. Like you stretch a rubber band, it breaks, snaps, releases this tension, and hurts your fingers, okay? And we think in particular there's a process called magnetic reconnection, where opposite field lines come together. And where they come together, they reconnect at many different points, forming plasmoids or magnetic islands. And we see these magnetic islands or plasmoids in a variety of astrophysical MHD simulations, from neutron star magnetospheres. Here are these little circular features, are the magnetic islands that form in the reconnection. Around black holes is a black hole accretion disk. They zoom in and they actually call it a plasmoid. And of course, we've been studying these phenomena in the sun for many years. Simulation of an eruption. So this is the eruption going out. We have reconnection happening in here, and many different plasmoids occurring in here. So what's special about plasmoids? Well, this is a really good mechanism for particle acceleration. How magnetic energy accelerates the ambient particles to relativistic speeds, which then deliver their kinetic energy to the lower atmosphere, causing an explosion. So I zoom in here. There are many cartoons that have been drawn over the years. to show this, illustrating the plasmoid process. Let's focus on this one. You have reconnection, oppositely directed magnetic fields. You have plasmoids, which are elongated. How do these accelerate particles? Well, you can attend Cole Tamburi's talk on Wednesday. So it's not the full story, though. We think there are several mechanisms that accelerate particles. Another promising mechanism is that there's a very fast outflow towards the sun after reconnection, and there's turbulence and stochastic acceleration. Also, there's possibly a termination shock, a shock down here where that outflow slams into the loops. Shock acceleration. It goes on and on and on and on. At the end of the day, we have a power law distribution of relativistic electrons that we think are produced in the corona, which stream down the magnetic field lines and deposit their energy in the chromosphere via Coulomb collisions, causing it to heat up to millions of degrees. That material then ablates into the loops. We call it an evaporation, causing the loops to shine brightly in soft X-rays. Another really interesting property is that we just don't have power law distributions of electrons. The sun seems to produce power law distributions of electrons with a very large number. It seems to accelerate almost all the electrons that are around into this power law. And this is one of the most highly debated aspects of the physics. Recent observations in the radio have shown a nearly complete evacuation of the corona during a different, more recent X-class flare. So we have these very dense particle beams, which then possibly stream down and impact the foot points. What evidence is there that these dense particle beams actually strike the foot points? We see a non-thermal source in the corona. We see a non-thermal source in the chromosphere. Can we connect the two? Is it reasonable to connect those two? OK, so here's direct evidence. This is a different flare. We have the G band, 430 nanometers, thermal response of the chromosphere. Very high resolution. We see a ribbon in the plage, a ribbon in the umbra, and very small area kernels. We get an area from this. On the right are the hard X-ray contours, 25 to 100 keV. This is where the electrons, the non-thermal electrons in the power law, emit hard X-ray Bremsstrahlung radiation, and also deposit their energy via Coulomb collisions, causing thermal response. So we can get a power from these contours. We have an area from that, and we can therefore get a flux density. I'm just going to call it a flux. Sorry, physicists. And what they get, this is one of the most important observations, I think, of the last 15 years, maybe even 20 years. They get a flux of 10 to the 12 to 10 to the 13 ergs per second per square centimeter in electrons above 18 to 20 keV. I'm going to refer to these fluxes as an F number, so F12 to F13 to save my breath. This is 2 to 3 orders of magnitude than what was used ubiquitously in the 1980s, 1990s, and 2000s, and what most modeling groups use still today. But not us. And then in other flares, you can convince yourself that you get large F numbers. One paper for this flare quotes an F number of 3.5 F11. I have convinced myself you can say this actually is 2 F12. If you're not afraid of that result. Why are we afraid of this result? Well, long story short, is if you have these huge high-density particle beam streaming in the corona, if they're produced in the corona and they're streaming through the corona, they propagate ahead of the accelerated protons because the protons are slower. And therefore, you have this charge displacement, a huge electric field. This electric field will then slow down the particle beam, all right? And the particle beam will be completely thermalized in a very short distance. So the particle beam won't even reach the chromosphere. And you won't even get this. And you won't get that. So this is a huge problem. So what do we do? Well, let us start somewhere, and assume that these high flux electron beams somehow get down to the chromosphere. Okay, it's a complicated problem. This beam propagation problem is very complicated. There's also instabilities that can come into play, as collisionless particle and cell simulations have shown. It gets really, really complex. So let's assume that these high density particle beams get down the chromosphere. What is the response of the atmosphere? What do the spectra look like? Do they look anything like the observations? Okay? So to do this experiment, we need an appropriate code that actually calculates a spectrum for us. That is, it solves the equation of radiative transfer, and it does it with a bunch of non-equilibrium physics. And the only code that I'm aware of is radian. It stands for, okay, it's radine. I say radian. It's my Midwest accent. Okay, radiation dynamics, radiation hydrodynamics. Originally developed to study shocks in the quiet sun, modified through various PhD theses to study flares. And here's why it's so awesome. It's 1D on the macro scale, okay, but it has a lot of interesting physics. Its energy equation has many, many, many terms. And it has many, many, many equations. So field and line flows, that's what we mean by 1D macro scale. Plane parallel radiative transfer. We resolve shocks. It has a really, really nice scheme to, for its adaptive grid. The time step's not limited by the Courant condition. In the transition region, to satisfy the Courant condition, if you do explicit, the time step would be so tiny. All right? And so if we're not limited by the Courant condition, what we do is we solve it implicitly. That is Newton-Raphson linearization and iteration with huge matrices. All right? It's truly radiative from photosphere to corona. No matter how many times I say this, I feel like half the people are still hung up on this. That's fine. Okay. We also solve the Fokker-Planck equation for non-thermal particle deposition with any number of force terms. Now, for the simulation I'm going to show, we only have collisional on. We want the particles to actually go to the chromosphere and see the response. And recently, I have incorporated accurate hydrogen broadening into radian. So I'm going to show you a simulation on the right of a high flux simulation, 5F11. And I just want you to notice a few things. You'll see the temperature response in black. This is the beam heating in red. In the bottom, the gas density initially is in green here. And you can see in hydrostatic equilibrium, it just decreases exponentially, approximately as expected. But during the flare, you'll see the transition region move inward, and then you'll see a pileup of mass below the flare transition region. That is the important part. This is over 10 seconds. Okay. Oh, I didn't loop it. Okay, so there's a pileup of mass. Peak mass is a factor of 10 larger than in the pre-flare. This is what we call a chromospheric condensation. The arrows show the velocities, obviously moving downward. And it's our hypothesis that These high flux beam simulations produce these chromospheric condensations, which then produce the near ultraviolet and optical spectral signatures that we observe. Okay, so that's the connection here. That's our working hypothesis. So for a variety of high flux beam simulations, this cartoon summarizes those types of movies. What we have, an electron beam hits the chromosphere. The low energy electrons cause a thermal blast wave. Heats it to millions of degrees. You have a sharp thermal pressure gradient, which drives material up, the evaporation. Sharp thermal pressure gradient drives material down into this condensation. It's about 25 kilometers. Okay, all the while, you have medium energy electrons supplying energy to the condensation. They can get all the way down there. The condensation starts at about 100,000 K, but as it accrues more density, it cools radiatively, but not as fast as if there were no beam. So you have a delicate imbalance between the beam energy supply and the radiative cooling. It's a highly non-adiabatic process. This is why radiation is so important for the problem. Okay, that's not the full story. The highest energy electrons of the beam heat a larger region just below the condensation, which is being swept up by the condensation, okay, also emitting optical near UV radiation. So it's just not the condensation that's producing the spectral signatures that we're interested in. And this is interesting because, yes, we have run F13 beams, and these seem to produce optically thick continua and model spectra that are very much in line with stellar flare observations. So how does this cartoon, these models, stack up against solar flare observations? So we looked at several solar flare spectra during a well-studied event, which had really nice iris observations in the near UV. Here I show a spectrum from the brightest pixel in this iris observation around an iron 2 line. Okay, there's an emission component around the rest wavelength. There's a redshifted component to this iron 2 line, which is broadened. And this is just an iron 1 line. You can just forget about that. The model evolution from the 5F11, which was from the movie that I showed, is the colored spectra. First, you have the beam lighting up the stationary flare layers, producing emission from material that doesn't have any velocity to it yet. The condensation at this point is 100,000 K, is not emitting any iron 2, it's just not at the right temperature. The condensation cools, accrues more density. Eventually, it shows up via the red wing asymmetry. It starts slowing down as it accrues more mass, gets denser, shines more brightly, slows down, gets brighter, accrues more mass. Okay, that's the evolution. Now, not a great match overall, all right, but let's get clever and let's average over an exposure time of 8 seconds to compare directly to iris. You can get clever and convince yourself that we win. Now, I want to point out that there is no scaling. I took the model, averaged it over 8 seconds, and put it right on here. These are intensity, absolute intensity units for both the model and the observation. Not bad for 1D models. Okay, so we thought we were winning around 2017, but then much higher cadence observations came along. The cadence of those data that I showed were once every 75 seconds. And then this flare observation came along, showing us the high time resolution evolution of the red wing asymmetry. The same iron 2 line. Emission around the stationary, emission around the rest wavelength. 9.5 seconds later, gets brighter. You start to see the broadened red wing asymmetry. Gets brighter. The red wing asymmetry gets broad and bright, less redshifted and less broadened, and then it merges together. So evolution over 45 seconds, about. And this is a really nice test case against our models. Because our models are time dependent, we can look in detail now. We can really test them one-to-one. No averaging, all right, over long exposure times. All right. I want to point out, though, the importance of high-cadence spectral observations here. Let's say we just had this spectrum, all right, and we didn't have these. What would you say? You'd say, OK, maybe this is one emission line. It's slightly redshifted overall. It has a slight red tail, and no one would ever care about it ever. But because you have the time history, you know that this red tail has a really prominent evolution before. Okay? All right. You see these two line components in different spectral lines, magnesium 2, carbon 1, and the far ultraviolet, silicon 2. And the far ultraviolet, we think the relative peak intensity between the redshifted component and the stationary emission component indicates not just the different temperature dependencies of the emission lines, but also the different optical depths. Larger lines with larger optical depths have brighter red-wing asymmetries. You have more emission from the chromospheric condensation, less intensity escaping from the layers below the condensation, from the stationary flare layers. I should say relatively less. All right, every flare has its own personality. We have hard X-rays for this particular flare. We can get a flux, F11, not that high. We have a power law index at 5. We can run a radiance simulation, compare. We find generally similar evolution as the 5F11, but overall much fainter. Okay? Some pretty striking discrepancies, though overall the evolution qualitatively is suggestive that we're on the right track with the interpretation in terms of a condensation and a stationary flare layer. Okay? Let's talk about how it's wildly wrong, because that's where we learn something now. First, the brightness of the red-wing asymmetry is way too bright compared to the brightness at the rest wavelength. Second, the time scale. This occurs over 45 seconds. This evolution occurs over 20 seconds. Model evolves too fast. Chromospheric condensation produces radiation that's too bright. And the third issue, which is not so apparent there, but is much more apparent in more optically thick lines, is that there's not enough broadening. There's not enough broadening in the model. Let me talk about the broadening first, which is going to tie in to the DKIST predictions. So Yingji Zhu is an undergrad student when he published his first author paper. He was a visiting student at NSO working with me. And he took a flare spectrum of the resonance lines of magnesium 2 after the ribbon had passed these pixels, and when the red-wing asymmetry had merged with the emission around the west wavelength. So you had broadened, nearly symmetric lines. And so he synthesized the profiles and found that the broadening in the models was way too narrow. All right. He took a look at the detailed collisional broadening theory in these models, found they needed updating from the 1930s theory to the 1960s theory, and that is the difference between the orange and the red in the top. Okay, still a factor of 30, too little. So then he was creative and multiplied the damping parameter, which controls the wing broadening, by a factor of 30. And you get the bottom panel. I think it speaks for itself. The red. Really nice overall wing shape in the model, also in the fainter magnesium 2 lines. He also messed around with a microturbulence parameter. So this is an adjustment to the Doppler broadening. Okay, it's an ad hoc adjustment to the Doppler broadening. He played with two supersonic adjustments, and these are the results. You can see, as expected, not very good because it's just Gaussian, and you have an exponential fall off and no enhanced wings. If you highly fine-tune this Doppler enhancement as a function of height, you get maybe something suggestive, but these fainter lines are way off. So what is going on? What is going on? Two possibilities we're leaning towards. This would make a great PhD project. If there's a student who wants to pursue these. Are we missing some deep chromospheric heating, which is where the wings are formed? Or are we missing some sort of collisional broadening physics? The collisional broadening I'm talking about so far is with the ambient plasma. What about collisions with the beam itself? This is a very, very hard problem and has not been solved. Okay, so this is unresolved. Let's go back to here. The rotating asymmetry, it's too bright. Are our model chromospheric condensations too dense? If only we had a spectral line that was very, very sensitive to the density in terms of its broadening. Well, we have many, and they are the hydrogen lines. So we have to go to the optical. So the hydrogen lines broaden dramatically due to the Stark effect, or the Stark-Lucido effect. So what happens is you have your degenerate energy levels of hydrogen, or a hydrogen-like ion, or Rydberg atom. In the presence of an electric field, they are split. Their degeneracy is lifted. So here, n equals 5 to infinity as a function of the electric field. And this is the Stark effect illustrated. Notice that for a given electric field, the splitting of n equals 5 is much less than, say, n equals 12. Okay? So that's a characteristic of the Stark effect for hydrogen. How do we know it's important in flares? Stellar flare observations. Here are two flares, two different M stars, looking at the calcium-2 resonance lines compared to H epsilon, Balmer epsilon. We see the Balmer lines get dramatically broadened, and the non-hydrogen lines, like calcium-2, stay really narrow. The sensitivity of the non-hydrogen lines to the linear Stark effect, collisional broadening, is a factor of 1,000 less compared to hydrogen. So why is the Stark effect interesting? And how do we include it in our models? Well, it's actually a very, very complicated problem. It's a beast of a problem that brings in plasma physics and hardcore quantum mechanics. We also call this pressure broadening or collisional broadening. And I want you to realize that this is broadening of a spectral line of a neutral hydrogen atom in the flare chromosphere. And the electric field is due to the ambient protons and electrons in the flare chromosphere because the flare chromosphere is partially ionized. Okay? It is not broadening due to the beam. So the protons and the electrons are moving around differently, so they contribute differently to the line broadening. And it's really difficult to combine these in a self-consistent way. The slow perturbers, the protons, have a quasi-static contribution. And they split the energy levels like this. Okay? This gives a Holtzmark profile to the line. The electrons are moving around really quickly. They cause an impact broadening, giving a Lorentzian profile. So you can imagine their broadening is like this. Okay? The important thing to realize, though, is you can't add these two independent processes. That is, you cannot do a convolution of the PDFs, 5550, because these are not independent processes. Why is that? It is because the electron collisions are non-adiabatic. That is, as an electron comes in, it can also knock an electron from one substate to another and therefore you need quantum calculations. Why does that cause a difference in the broadening? Well, it decreases the lifetime of any substate. Decreases the lifetime by the uncertainty principle, increases the energy width. Ugh. And that transition probability is obviously dependent on the amount that they're split initially. There are two widely used theories that do this correctly, or full quantum theories. The unified theory, which has been updated to include non-ideal effects and used in state-of-the-art white dwarf atmospheres. This is the theory that we use. So I'm not going to, for the sake of time, I'm going to skip over this, but it's been a question for 25 years of how to incorporate approximations into radiative transfer codes using Voigt profiles. First pointed out in John Kroll, various approximations are here compared to the actual quantum theory, the thick line with the circles that we now have in radian. So how does this make a difference in our models? Predictions for the DKIST, H-alpha line. This is our 5F11 beam heating model. The H-alpha line at some snapshot, 4 seconds into the heating, when the condensation is really dense, around 10,000 K. Before our update is the dashed line. It's entirely redshifted due to the condensation motion. It's somewhat broadened, but the updated broadening, the thick line, is also entirely redshifted, but much broader. We don't have much observations for sanity checks. I scale a line scan from an X-class solar flare, shown as the pink, and then I apply a constant offset in intensity to show you that we might be on the right track here. We want to go farther out in the wings, obviously. And for that, we need the VISP, the visible spectral polarimeter on the DKIST. And in fact, I show a wavelength range for a VISP spectral window here. This is what we can do. We can test these models. All right, H-alpha. I would prefer H-gamma. Farther in the blue, more optically thin, closer to LTE. Results from 5 to 2 instead of 3 to 2, so it's more stark broadening. Here's the evolution. First, you have emission around the rest wavelength with a slight red tail. And then the line becomes entirely redshifted and highly broadened. Then it becomes fainter, and fainter, and becomes even more broadened. Now, I've described this in a lot of detail in this paper here. And to understand why it becomes fainter and broadened and less redshifted over time, we need to analyze the contribution function to the emergent intensity. I'm just going to point out a few things that we can take away from the contribution function. So this is the contribution function. Where it's bright, it shows you where in the atmosphere the emergent intensity originates. And you can see this is a log scaling. So it's very bright in a very narrow layer. That's the chromospheric condensation. Height of 0 is the photosphere. Condensation is at 900 kilometers, and it's descending downwards. So this line is very optically thick. Most of the intensity originates from a narrow layer, from a very high density, 5 times 10 to the 14. This is a much higher electron density than has ever been discussed in a solar flare chromosphere. Also, it's not just electron density, charge density that's broadening these profiles. There's also optical depth effects. And that's very important. You have to model the optical depths through the condensation and the electron density simultaneously for proper interpretation. Okay, that's a general slide that summarizes the low order hydrogen lines. H alpha, H beta, H gamma. These are very optically thick. Okay, they're entirely redshifted, highly broadened. Yes?
Adam, how are the hydrogen lines formed?
It's collisional, yeah. The condensation becomes so dense that collision rates are very, very high in these condensations. Yeah. H alpha is farther from LTE. So you have more scattering involved. But there's not much recombination cascading going on at all. It's mostly collision excitation. OK, let's look at the higher series members, farther in the blue near the Balmer limit. This is, to me, maybe the most interesting result from the paper, though it's buried deep around page 364. I'm just kidding. It's only 20 pages long or something. All right, so here's our spectral prediction from that same time stamp at 4 seconds, where the H gamma line was redshifted by 40 kilometers a second, the speed of the condensation. The higher order Balmer lines are not. Also, if you look at their widths, they're narrower than H gamma. But the Stark effect says these lines should be much broader than H gamma. What the heck is going on? The answer is like so interesting to me. So the condensation is so dense that you have non-ideal effects. The upper levels of those transitions are dissolved. They don't exist. So you have a gray opacity window at these wavelengths in the condensation. You have like a translucent window down to the stationary layers that are heated less, have lower electron density, give smaller broadening. Compared to archival observations, decent. Now, we have these predictions, right? What happens if DKIST comes along and it's like nothing matches with H alpha, H gamma, H beta, like nothing's even close? Do we have an alternative hypothesis? Right? We have these high flux electron beams. I have said nothing about the resolution of the transport problem. There is an overlooked calculation that I think is the answer. Contour et al., 2012, solved the time-dependent Fokker-Planck equation simultaneously with plasma waves, electron plasma waves, Langmuir waves, and ion acoustic waves. These are just really basic plasma waves. And there are really interesting interactions among the plasma waves and the beam itself. And what you have is the lower energy electrons transfer energy to the plasma waves, which then interact with themselves and then boost a lot of energy to the higher energy electrons. So the initial electron distribution is the teal. So we have 10 keV, 100 keV. It's a power law index of 4. And the modified transport results in the distribution as so, with many more electrons at 100 keV and above at the expense of the lower energy electrons. I'm about to submit a paper showing the difference in heating rates. Now I show the calculation of the heating rate. This is the chromosphere. This is the photosphere. This is more or less what I've been showing previously with the heating rate peak at -4. The modified distribution now is a heating rate at a factor of 100 deeper column mass. This is really, really exciting because this is the column mass that you need to heat to 10,000 K to produce optically thick continuum. We have observations from stellar flares that we can compare to this modeling approach. And we think that we need optically thick continuum to explain these observations. And it turns out that we've already developed a semi-empirical radiative hydrodynamic approach with more or less this beam heating distribution as the Contour et al. Prediction independently. And that's the point of this AppJ letter. By matching to M-dwarf flare observations and using radian, we have used high beam fluxes. We have put the minimum energy in the beam to 80, 100 keV. And we get essentially contour beam heating. However, interpreting stellar flares is difficult because you're not looking at one pixel, but you're looking at flaring from many different regions whatever is flaring on the surface, because it's spatially unresolved. So I'm going to show you how we can approach this problem. We can use solar flare observations. I'm almost done here. We define a high intensity threshold, kernels. We define a medium intensity threshold, diffuse ribbons. Area ratio of 5:1. We have a kernel model in purple, which primarily generates the continuum and broad emission lines. We have a diffuse ribbon model, primarily the narrow emission line. We add them in the area ratio of 5:1 and compare it to a very famous M-dwarf flare spectrum, super flare spectrum in black, from 360 nanometers to 440 nanometers. And that's the blue, the superposed model. We actually do a linear least squares fit of the two areas, and we get that. We get the area ratio from this. So we do it independently. Here's a zoom in of the H-gamma line. The linear least squares fit of the two model components is shown as the circles compared to the data, which is the histogram, very broad H-gamma line. And then the Balmer series merging. Pretty good matches here. However, we need reality checks. And our reality checks will be the DKIST. We want to put our slit along a flare ribbon. We want to determine if the very broad H-gamma profiles and continuum comes from the compact kernels, and the more diffuse ribbon emission produces the narrow line H-gamma emission. So here I show that flare kernel. I took the DKIST to the sun. Or I took Iris to the sun, looked at Hurricane Teddy. That's what I saw. I took the DKIST to the sun with the spatial resolution of the VISP, looked at Hurricane Teddy. That's what I saw. We'll be able to really see dramatic details in these kernels, okay, and determine the difference in broadening from place to place. We're beginning to look in detail at the broadening using higher resolution observations of M-dwarf flares. This is a kernel model. However, before we go willy-nilly and apply this two-component fitting to all of these M-dwarf flare observations, we really need these reality checks. If I start applying this technique with this kernel model to solar flares, I start to see better agreement in the red wing asymmetry of iron 2. And then finally, I want to point out ₦uxes flare campaign, maybe the largest ground-based flare campaign data set ever, using data from the telescopes at Apache Point Observatory. We just don't see symmetric broadened hydrogen lines in flares. We see a variety. We see blue shifts, we see red shifts, we see blue shifts, then red shifts, shown here for a flare in YZCMI. So I'll end there. Thank you for your time.
Thank you, Adam, for such an interesting talk. Questions, please. Okay, yeah, Rahul. Yep.
Okay, so in gradient simulation, you showed that within 30 seconds,
Oh.
the line shifts, right? So my question, what is happening to the line formation in that period?
Sorry,
The formation height of that line.
yeah.
What is happening to the formation region?
When it's shifted by 40 kilometers a second? Yeah, so that's when it's being entirely formed in the chromospheric condensation, which is a dense accretion of material that's flowing towards the photosphere at that speed.
So my question is about the formation of that line, because the line is forming at some height, right?
Oh, yeah.
Is it changing during that time, or is it stationary?
Oh, yeah, it's following the condensation.
Okay,
Yeah.
following the current.
Right. It's yeah. As the condensation gets denser, it's becoming more optically thick. So it's like it's stuck to the condensation evolution.
My second question is,
Let's give time to someone else. Yeah, go ahead.
So kind of following up on Tom's question, where you said the cooler lines are going to be moving down toward the photosphere, and the hotter lines are going to be flowing out toward
Yeah,
us.
right.
If you simplistically think of there being like some temperature where
Yeah.
everything on one side goes up,
Yeah.
everything on one side goes down,
Yeah.
time evolve during the flare?
Yeah.
Transition temperature.
It's a really good question. Yes, because of the evolution of the condensation. Okay, so the condensation starts at 100,000 K, all right, and so you'd have redshifted lines at 100,000 K, but it cools to 60,000, then 40,000, and so eventually you wouldn't have lines at 100,000 K being redshifted at those later times.
So with time resolved spectroscopy, you could map that.
Correct. Yeah. And so this demarcation has been seen in the sun actually. The temperature at which the transition goes from blue shifts to red shifts, and is about at what our models show, give or take, several tens of thousands of degrees.
And I'll take one last question. Yep, I'm right.
Hey, so I haven't done much solar flares or radiative whatever. So for those of us who are not solar flare experts, why is it such a big deal? You made a very big point at the beginning of your talk about how power laws everywhere.
Power laws?
Why is
Yeah.
that such a big deal? Why does that matter?
Power laws are